Ну хорошо. So let's start. Please interrupt me whenever you want. So what we did last time. So we discussed Néron-Severi group of product of two curves over the field of complex numbers, and we observed that the Néron-Severi group can be identified with endomorphisms, graded endomorphisms of the Hodge structures. So this is X. So you have H0, H1, H2, H0, and H1, very simple groups. So this is so this has two copies of Z in it, right? Да. Thank you very much. Okay, so this was the main observation from the last lecture, and I also want to show that this Hodge structure, this endomorphisms in the category of Hodge structures can be identified with Z times endomorphisms of the Picard scheme times Z. So what we want to show is that this is what we want to prove, and showing that endomorphisms in the category of Hodge structures of H1 of X is precisely endomorphisms in the category of group schemes of the Picard scheme of X. And to this end, we describe this Picard scheme as, well, it's underlying analytic space as follows. So we have group scheme. We have the underlying sort of Lie group, complex Lie group. And we have the exponential map. This is holomorphic map from its Lie algebra. Well, it doesn't matter whether I put here algebraic or analytic, but let's do this. And so this Lie algebra, well, it's a vector space, which is the tangent space to the Picard scheme is always this. So therefore, we get a holomorphic map from a vector space to this Lie group, and because this group is commutative, the exponential map is a group homomorphism. So it must be surjective because the derivative of the exponential is equal to 1 at one point, so the image is open, and because it's a group homomorphism, it must be also closed. So this map, identifies, induces an isomorphism between the Picard analytic group, this Lie group, and the quotient of H1 of X, this coefficients in O, modulo H1, modulo the lattice. It's the kernel of this homomorphism. This is a nice. No, this is group homomorphism. So just homomorphism in the category of groups, right? Endomorphisms, preserving the addition.
Thank you. Why, maybe this is a too big question, but why the tandem space of Picard group is H1?
Very good question. So why the Lie algebra to the Picard Picard is, well, it doesn't matter whether I take connected component or just the entire Picard group, or say connected component is H1 of X with coefficients in O. Well, if you, this is where actually scheme theory is very useful. Picard schemes, for at least for curves, or well, they're known under the name of Jacobian, were constructed by Riemann Abel in 19th century by kind of explicit construction. So you have first to construct a manifold, and then, if you are lucky, you can compute its tangent space. But in modern language, one first defines this as a functor it represents, and then proves that it's representable. So what is the functor it represents? Okay, so let's, first of all, let's write down definition of this Lie, of the tangent space. If you have any scheme, then its tangent space is, by definition, the set of maps from the dual numbers to Picard. Let's call it phi, such that the restriction of phi to spec k, right? I have a closed point here, spec k, is 0. 0 is the neutral element here, right? So that's what I want to. Now, what is this? So these are, so what are maps from a scheme to the Picard scheme? By definition, these are line bundles on X tensor with spec k of epsilon, right? Modular the Picard group of this base. Yes? What are morphisms from a scheme to the Picard scheme? Я еще не... Сейчас я... Okay, I will first finish. Okay, so kernel, I claim that this is the same as the kernel of this map. Okay. So every element here gives me a map, phi. Conversely, there is a one-to-one correspondence between the group of such maps and the Picard scheme. Well, it's just isomorphism. The group of such such phi is isomorphic to this, right? Нет, значит, я утверждаю, что вот просто группа отображений из этой схемы сюда, она изоморфна вот этой группе. Да, но там нету у k от эпсилон группы пикара равна нулю. Правда, любое линейное рассвоение на спектре k от эпсилон равно нулю. Ну, вы совершенно правы, что я должен был бы отфакторизовать, конечно, потому что вот такой функтор представляется. Но я это как бы игнорирую, потому что эта группа равна нулю. Хорошо? Угу. Спасибо. Okay, so that's what we want to compute. And Lisa, so is it clear? Okay, and now this is the same as the kernel of the map from H1 tensor with spec k of epsilon to this group. These are the same, the underlying topological spaces are the same, but the sheaves are different. And so now you just, in order to evaluate this, you look at the short exact sequence, or I will write it here, O star x tensor at spec k of epsilon goes to O star x, right? So the underlying topological spaces are the same. Therefore, I can think of this as kind of sheaves on the same space. And what is the kernel? Suppose I have an invertible function here, and, well, I can restrict it to the closed subscheme here. Objective, because it has a splitting. If I have a function on x, invertible function on x, I can pull it back. So it has a splitting. And what is the kernel? Suppose I have a function, invertible function on x times this guy, which is equal to 1 at epsilon equal to 0. What? So I claim that the kernel is going to be 1 plus OX times epsilon. So if I can, this is an example of an invertible function here, right? Remember that epsilon squared is 0. There is a, okay, and as a sheaf of group isomorphic to AX, right? Because you multiply this function, well, it's right, because epsilon squared is 0. So we see that the kernel is precisely first homology of this, because it's a split exact sequence. So this group is direct sum of these two. Okay, so does it answer a question? So we computed the Lie algebra and identified it with this. Very good. So now I want to use this to show that endomorphisms of this scheme, or the same of this Lie group, is the same as endomorphism of this Hodge structure on H1. Okay, So, so let's compute endomorphisms of this abelian Lie group. So this will be H1 of X modulo H1 XZ. So I think of this as a Lie group, and I want to, see what are the maps, homomorphisms from this Lie group to itself. So, so let's again look at this exponential map. If I have any map phi here, phi, right, then it also acts on the Lie algebra. That's going to be the differential of phi. Let me call it psi. So it defines, and this this differential, these two actions commute with the exponential, right? So therefore, so I have I can identify this with all linear maps. So psi is a linear map from the Lie algebra to itself. The Lie algebra is commutative. So this is just psi in acting on H1 on this vector space over complex numbers. And what is the condition? So suppose I have endomorphism of vector space. When does it descend? So this is a surjective map. So that means that phi is uniquely determined by this psi. Right? So what is the condition on phi, on psi, which guarantees that it descends? So you have an endomorphism of this vector space, and my question is when it descends to the quotient. Clear? Но если у вас есть любая группа Lie, то у вас есть всегда отображение из алгебры Lie в группу. Okay, so so that's I mean I don't really maybe the following answer will satisfy you. So there is a map. The answer is provided. Okay, so there is a map. So here is another description of this exponential map. So this group maps to H1 of X with coefficients in O star. I will write it here. This is analytic. And its image lives in the kernel of the Chern class map. Right? So, and this kernel is precisely is precisely the peak zero. So this exponential map is simply induced by this map, which also not surprisingly called exponential, right? Which just takes an analytic function and takes it and carries it to its exponential, right? Ну, значит, для коммутативных групп что такое экспоненциальное отображение? Это отображение из алгебры Ли, это гомоморфизм из алгебры Ли в группу, который обладает тем свойством, что его производная в единице тождественна. Вот. Значит, с помощью этого можно проверить, что вот экспоненциальное отображение вот в этой группе Ли совпадает с этим. Ну, мы как бы так отождествили касательное пространство к этому, что оно стало вот, в общем, это становится, это более-менее тавтологичное утверждение. Хорошо? Значит, экспоненциальное отображение, еще раз, оно характеризуется однозначно вот этим свойством, что это гомоморфизм и что производная в единице тождественна. Хорошо? Okay, so the condition now is that psi preserves the lattice. Psi of h1 of x with coefficients in z belongs to h1 of x with coefficients in z. Right? Good. So very simple linear algebra description, and now I want to identify it with the left-hand side here. And in order to do this, let's recall how this Hodge structure is constructed. So we have h1 of x with coefficients in z. This maps, this is the lattice here, so it maps to h1 of x with coefficients in O. Explicitly, it's just given by the inclusion of z into this sheaf. And because this is a complex vector space, any such map extends to a map of complex vector spaces by linearity. So this has dimension g, this has dimension 2g. It must have a kernel, and the kernel is precisely f1. Global f1. And that's our definition of f1. Now, so what is the endomorphism? Looking at this short exact sequence, so what is what we have here? So by definition, an endomorphism of a Hodge structure is an endomorphism of this lattice that preserves such that its complexification, right? So you have an endomorphism here such that its complexification preserves f1. And therefore, it defines an endomorphism here. Okay? So, now I think it's clear that this is the same as endomorphism of Hodge structures of H1. Again, so once I have psi, I consider psi tensor identity, which acts here. It also acts, I have this map descends to quotient, and therefore it preserves f1. Да, да. And therefore I have psi acting here. So this gives me a map from this set to this set, and conversely, if I have an endomorphism of this lattice that preserves F1, then I therefore it then descends to the quotient, and this is my psi. This gives me one-to-one correspondence. Okay? So this completes the proof of this isomorphism here. So in particular, over the field of complex numbers, I have a complete proof of the fact that this Néron-Severi group is this. And this gives a ring structure here. And we also get this group. This is a ring, but merely as a group, it's a free abelian group of finite rank, because this is a sub-ring even of the endomorphisms of H1 of X with coefficients in Z. So this is a subgroup, sub-ring of the ring of matrices with integer coefficients. So it has finite rank. So
what is sort of the expected rank? So we know that if X is like a general elliptic curve, then it's
1.
Yeah, so in general, it's just
1. That's a very good question. It's not easy to answer. Well, it requires some work to prove it in general, because we don't know what are the Hodge structures explicitly that come from curves. But if genus is 1, then, any Hodge structure of rank 2 comes from a curve. Namely, you just take the can take this quotient, and this is going to be a torus, two-dimensional torus. So it's complex one-dimensional torus. So that's an elliptic curve. And then it's an easy exercise to show that for generic curve, the endomorphism is just Z. Okay, so here is an exercise.
Correspond to abelian varieties. Those tori who are an association of abelian varieties. And
Say it again.
well, Hodge structures.
Hodge structures correspond to abelian varieties. So namely, okay. So Hodge structures, the category of abelian varieties is embedded into the category of Hodge structures, right? So if you have an abelian variety, you can take H1 with coefficients in O. You have the Ram homology with Z coefficients. So this exponential map for the abelian variety gives an embedding of the category of abelian varieties into the category of Hodge structures. But the image is the image is not everything, so you need extra condition on this Hodge structure. But most importantly is that curves, you have fewer curves than abelian varieties. Every curve gives rise to an abelian variety, namely peak 0, but it's hard to characterize those abelian varieties that come as that appear as Picard group of a curve, Picard scheme of a curve. So here is an exercise. Important exercise, which is not difficult, but it uses, nevertheless it's important. So for any alpha in in endomorphism in the category of Hodge structures of H1 of X, the trace is greater than 0. Well, provided that alpha is not 0. So I stated this, well, remember that this trace is the same. So if you think of this endomorphism as a element of the Néron Severi group, then this trace is the same as intersection, self-intersection of alpha, up to negative sign. So this result can be obtained as a corollary of the Hodge index theorem, right? So you have a cycle on X times X. It's orthogonal to, because it lives here, it's orthogonal to the class of... Мы обсуждали, что это следствие теоремы Ходжа об индексе. Но я предлагаю доказать это непосредственно следующим образом. Вот это утверждение. Теорему Ходжа об индексе. Она очень простая. So how to see this? So not to confuse it, I will erase it. So it will be direct proof of the Hodge index theorem, which is a non-trivial result. Okay. So what can you do here? So let's alpha t. Alpha t is the adjoint to alpha with respect to Poincare form on H1. Right? That's definition. So you take, this has Poincare form, you take the product, and you take the trace. So I want to show that this trace is positive. Of course, it's not true that for a symplectic vector space, this is positive. However, so here is a hint to this exercise. Let alpha star be the adjoint to with respect to the positive definite Hermitian form on H1 of X with complex coefficients. So remember that we did, so what is the form? So it was, if I have a class gamma in F1, then the form gamma prime is integral of gamma prime bar multiplied by I, and and also well, it's if gamma and gamma prime are in F1 bar, then the form is also given by the same formula, except that I have negative sign, negative I, gamma prime bar. Okay? So we have, first of all, we have this Hermitian form on the entire space. It's not positive, but it's positive on 1. And it's on F1 bar. So by changing sign here, I can make it positive. Yes? So this space has a positive definite Hermitian form. So if you have a positive definite Hermitian form, then for any alpha, trace of alpha star composed with alpha is greater or equal than 0, right? Because if you have a positive definite Hermitian form, you can just take an orthonormal basis, and then this amounts to the fact that the trace of, for every matrix, A bar TA is greater than 0. Right? So we know that this is greater than 0, and now да. Потому что, ну, утверждение. Допустим, что у меня есть векторное пространство с положительно определенной эрмитовой формой. Любой его эндоморфизм – это сопряженный. Тогда я утверждаю, что след больше нуля. Доказательство. Хорошо? Да, да. Now, check. So here, alpha can be any endomorphism of this complex vector space. Now, check that if alpha is an endomorphism of the Hodge structure, that means that it preserves, in particular, this decomposition. Then alpha t is equal to alpha. So the adjoint with respect to this positive Hermitian form coincides with the adjoint with respect to the skew-symmetric form. Okay? So this is positive for every alpha, and for alpha here, alpha star coincides with alpha t. So a hint why it happened, right?
Альфа Т это двойственное относительно.
Спаривание Пуанкаре, косимметрия. Спаривание Пуанкаре в наших обозначениях это вот такое. Интеграл от гамма, гамма-штрих. Что здесь надо использовать? Что, во-первых, альфа вещественна, то есть, потому что она даже целочисленна, она сохраняет целочисленную решетку, поэтому она сохраняет целочисленную структуру. А во-вторых, то, что она сохраняет, это разложение. So this is a proof of the Hodge index theorem. This case. Now, here is one more observation that I want to make. So let's return to the, observation. Here is this formula for the Picard. So Picard, peak 0x, analytic, is h1 of x with coefficients in O, modulo h1 of x with coefficients in z. Okay? This formula implies that so let's look at the torsion points of order n in this group. So I will put n here, and this is by definition kernel of the map. From the pcar of x to the pcar of point order n. So we have a very explicit description of this group. It's just this. So we have a complex vector space, we have a lattice. We want to compute torsion points in the quotient. What are the torsion points in the quotients?
1 over n.
Very good. Very good. So this is 1 over n h1 x z modulo h1 of x with coefficients. Is it clear? Good. And this is the same as h1 of x with coefficients in z mod n z. By definition. Oh, we have. So that's the definition. And now I will also make another definition. So, so here we defined homology with torsion coefficients. I would love to have kind of an algebraic definition for this group, but I don't know how to do this, how to, well, a reasonable candidate for this. You can argue that it doesn't exist, but anyway, so I don't know how to make sense of this. But what we can do, we can define homology, a Ladze homology. So for every prime number L, we can define this group, and it's by definition just the inductive limit over M of groups with finite coefficients. And I have twist by 1. And here I also have twist.
Что это значит вообще?
Что?
Сдвиг на единицу.
Мы скоро будем, если нас просто интересует это как группа, кривая у нас над алгебраически замкнутым полем, то не значит ничего. Но представь себе, что у тебя, скажем, кривая определена была изначально над рациональными числами. Ты ее берешь над алгебраическим замыканием рациональных чисел и смотришь на точки конечного порядка на пикаре. Тогда на этих точках действует группа Гула.
Да, нужно взять инварианты.
Ну, нет, я же не нужно брать инварианты. Я хочу брать точки в пикаре, но над алгебраически замкнутым полем, чтобы их было много, иначе их может быть очень мало. Но тогда на этом множестве действует группа Гула. И вот сдвиг на единицу означает, что ну вот есть как бы вот такие вот когомологии. Они отличаются от этих подкруткой на одномерное представление группы Гула на корнях из единицы. В общем, это означает, это как бы...
Сейчас, но если у меня поле не замкнуто.
Да. Я не хочу, вот это определение я не хочу применять это к кривой над незамкнутым полем. Я хочу сначала перейти к алгебраическому замыканию, сделать замену базы, и там взять точки конечного порядка в пикаре. Я получу абелеву группу, но теперь я помню, что моя кривая изначально она пришла заменой базы с кривой над меньшим полем.
Да.
И как я это помню? Вот на этой конечной группе будет действовать группа Гула.
Да.
Вот сдвиг на единицу означает подкрутку на одномерное представление группы Гула.
Что значит подкрутку?
Ну вот z от единицы это проективный предел zl от единицы μ l в степени m. Значит, вот эта вот группа, она, если L взаимно просто с характеристикой, она не равно характеристике. Она как бы абстрактна, как группа, да? Ну, сколько у меня корней из единицы? Ну, если L не равно P, над алгебраически замкнутым полем их ровно L в степени m штук.
Нет, я понимаю, что абстрактно получится то же самое.
Да, абстрактно.
Я не понимаю, каким образом эта подкрутка помнит изначальное поле, если оно было не замкнуто.
Значит, сейчас, ну, я даже не знаю, как формализовать вопрос. Просто если вот такая, она отличается от этой тензорным умножением на одномерное представление группы Гула.
Давайте так. Вот какие объекты математики вообще могут ставить справа? G-модули, где G это абсолютно группа. Да. Но если, вот так как сейчас это написано, это не имеет смысла, у нас поле алгебраически замкнуто. Но потом мы будем это применять к многообразиям, на которых есть структура над меньшим полем.
И в целом мы умножаем на это представление просто, что у нас справа стоял G-модуль.
Да. Нет, просто он будет другой, да? То есть есть вот так, есть такой же модуль, а есть такой же модуль.
Если мы не домножали, то там как бы тривиальное было бы действие.
Нет, абсолютно не тривиально, он просто был бы немножко другим. Это вопрос обозначений.
Ну хорошо, ладно.
Okay, I will maybe comment this. Like.
Мы увидим потом, почему так надо.
Ну, мы дадим определение вот такое, и чтобы оно было согласовано с этим, нужно подкрутить на действие группы Гула на корнях из единиц. Да, это мы увидим. Okay. So what are the results here? Okay, maybe before I let me again make this remark, which is, I think it's clear. So if K is C, then this first étale homology of X with coefficients in ZL of 1 is just usual homology, Betti homology, with Z coefficients, tangent with ZL. That's the picture that we should keep in mind. So we give a geometric description, algebraic description, which doesn't refer to base field, not of this group, but of its tensor product with ZL for every L. So now, so here is a theorem. Maybe, yeah, before I can state. So we have the Néron-Severi group, which, as we already know, for any field, it's isomorphic to Z times endomorphisms of the peak 0 as a group scheme times Z. And now this group maps to, well, I will say endomorphisms of H1 et al. Of X ZL of 1 times, well, to make, this is a ZL module, so to make, let me put ZL also here. So there is a map like this. So how this map looks like? So what is its definition? So this is just the embedding. And this map here is obtained by functoriality. So if I have a homomorphism, endomorphism of the Picard scheme, of course it acts also here. It takes n torsion points to n torsion points. So it acts on the entire picture, so it gives me this by functoriality. It gives me this map. So this is the analog of the embedding of this Néron-Severi group into endomorphism of H1, H2, and H0, H1, and H2 that we had over complex numbers, right? Over the complex numbers, we also describe the image of this map as those endomorphisms that preserve the Hodge structure. So now the theorem, well, suppose that L is not equal to the characteristic of the field. Well, for example, the field has characteristic 0. Then H1 of X, this is theorem of also of Weil. H1 et al. With coefficients in ZL of 1 is a free ZL module of rank 2G. G is usually the genus. And the following is true. the trace for every alpha in the Miron-Severi group of x times x, the trace of alpha, and remember that the trace of alpha is the intersection of the cycle with the diagonal, is computed by the Lefschetz formula. So it's equal I equals 0 to minus 1 to I of traces of alpha star acting on H1 et al. Hi. Well, I didn't tell you what H0 and H2 are, so this, therefore I put quotation marks here. So the formal statement is that this is its action of alpha on H is you take alpha and intersect it with x0 times x. This is the vertical line. Then subtract the trace of alpha star on acting on H1 et al. And you add alpha x times x0. Okay? So you should think of this number as an analog of the trace of alpha acting on H0, which I haven't, well, it's as a space, it's just DL. It's not very interesting. But nevertheless, it might have non-trivial action of alpha. So this is this number. And the action of an H2 should be related to the degree of alpha. So that's this intersection. So really, you may ignore this, and the precise statement, the formal statement is this formula. So this is the analog of the Lefschetz formula. Now at least I can give I can state it formally. So so this formula can be proven, and it was proven directly by Weil. The proof is not very difficult, though it requires work. It would take me another 2 hours to prove it. But I, instead of giving a proof for curves now, I will postpone the proof. We'll give a proof of more general formula for a Tal homology of any smooth projective variety, and this will be a corollary of that more general Grothendieck-Lefschetz formula. So I will postpone the proof. But now I want to, instead of giving a proof, I want to derive a corollary of this. So corollary. So corollary is the following. Suppose you have from the curve to itself a finite map, and its degree is some number q. Then the characteristic polynomial of f star acting on H1 x ZL1 has integral coefficients independent of L, which is not equal to the characteristic. So this is not at all obvious because, so if you just stare at this definition, well, any endomorphism of any map from X to X, well, of course, it gives some, it induces a map here, but so, well, you get a ZL linear endomorphism of vector space, so characteristic polynomial a priori has coefficients in ZL. But I claim that they are actually rational integers. And moreover, that they are independent on L, which is also not at all obvious from this definition. Yes? Да. Ну, мы группу нейрон на севере отождествили с вот таким прямым произведением колец. Кольцо Z, кольцо эндоморфизмов схемы Пикара и еще одна копия Z. Да, если у меня есть элемент эндоморфизм Пикара, то он, конечно, здесь действует, потому что он действует на точках n-того порядка, да, любой эндоморфизм этого дела, этой схемы, действует на точках n-того порядка, поэтому по этому определению он действует и здесь. Хорошо? Окей. And its roots have absolute value q to the 1/2. Okay? So let's prove this. Derive this corollary, we will use everything that we learned so far to derive this corollary. And this is kind of the summary of, well, it was shown by Andre Weil, and so Grothendieck and Deligne generalized this corollary to the case of any.
The action is as follows. You take the action of f as a Picard group,
Yes.
and you restrict to torsion points.
Yes.
But didn't we just discuss that 99% of the time the action is just multiplication by, because it has no other element?
That's a very good point. However, this is what you said is true over the field of complex numbers. Though even over the field of complex numbers, you have even some elliptic curves with complex multiplication, something. But in characteristic P, you have the Frobenius morphism, which is not necessarily multiplication by a constant. So in characteristic P, you have more endomorphisms. Typically, this endomorphism is not liftable to characteristic 0. Well, it's for genus greater than 1, it's never liftable.
If x is defined over a finite field.
Yes. Well, it's always, if x is over fp bar, then it's definitely, it comes by base change from finite field, so you have this Frobenius endomorphism.
If it's defined over some larger field of characteristics,
Characteristic 0, then it still may have no endomorphism at all.
and usually would. So this is like interesting mostly in the case when x is defined over finite field.
Well, no, there are some, usually curves with larger group of endomorphisms are the most interesting. So if you apply this result to then you recover the Weil conjectures. So, okay. So let's give a proof. So let f be the characteristic polynomial. So what do we know about this this polynomial? First of all, if you from the Lefschetz formula, sorry, I have erased it. I shouldn't have done this. So I have to repeat it again. So if you take the trace of alpha, which is alpha gamma f, I want to apply the Lefschetz formula to the graph of f. And if you intersect it with the diagonal, then the Lefschetz formula that I just erased shows that this number is equal to intersection of gamma f with x0 times x. And because this is a graph, this number is equal to 1 minus trace of f x h1 et al. Plus gamma f intersected the vertical line. Right? And what is this number? Degree. So this is my Q. So if I apply the Lefschetz formula from this Weil theorem, I have that this intersection is 1 plus Q minus this trace. And in particular, it follows the trace of f of gamma f acting on, sorry, of f acting on h1 et al. Are rational numbers. Is a rational number. Well, actually, it's an integer, right? Because this is an integer, this is an integer, this is an integer, right? So, and applying the same observation to powers of f, we see that these traces are also integers, right? You can replace f by its nth iterate. So for every n. Катя, из этой формулы, потому что в этой формуле все везде целые числа, за исключением n. Okay? So suppose you have a matrix whose such that the traces of its powers are integers. Well, at least you can conclude the coefficients of the characteristic polynomial are rational numbers. So this polynomial is rational coefficients, right? Because, so coefficients of the characteristic polynomial can be expressed in terms of the traces of the power of matrices. These are Newton polynomials. These traces are Newton symmetric polynomials in eigenvalues, and the coefficients are elementary symmetric polynomials. They express one in terms of the other of rational numbers. So at least we proved half of the statement. So now let's check that these coefficients are actually integral. This is not entirely obvious. So why it's not obvious? What is the trace of the coefficients of the characteristic polynomial are traces of the symmetric powers, exterior powers of f. What is the trace of the exterior power of f in terms of the trace of f and f squared?
Eccentric
I think it's trace of f squared minus trace of f squared divided by 2. Everyone agrees with this? Well, if you have eigenvalues, lambda I, then this number is lambda I j sum I greater than j. So the number you have here is lambda 1. So this is sum of lambda I squared minus lambda I squared divided by 2. That's the formula. So you see that you have some denominators here, but now let's check that they are rational coefficients. So now so here I'm going to use the fact that the neuron severity group of every smooth projective variety, in particular of a surface, is known to be have finite rank, has finite rank so this is a ring which as an abelian group, it's a free abelian group of finite rank. Therefore, gamma f, view it as an element in this ring, is integral. All right? What does it mean that an element of a ring is integral? It means that it satisfies a monic equation, algebraic equation, with integer coefficients. So it means that there exists a polynomial m of t with integer coefficients. And this is monic. Such that n of gamma f is 0. Right? How do you see this? You just look at the multiplication by gamma on this ring. Is a abelian group of finite rank, and its characteristic polynomial, which now has integer coefficients, right? Because it's a free abelian group. You just write the left multiplication as a matrix. And then by Cayley-Guillemington theorem, it annihilates gamma f. So, and this implies, because we have a ring homomorphism from the neuron severity group to the endomorphisms of this space, right? It implies that n f star, view it as an endomorphism of H1 et al. X ZL is equal to 0, right? Because we have ring homomorphism from the neuron severity group to this ring. Does it make sense? So what we learned is that this f, well, it's minimal, well, at least it's annihilated by some polynomial, monic polynomial with integer coefficients. Therefore, its roots are algebraic integers. Roots of f acting on H1 Etal X ZL are algebraic integers. In particular, the coefficients of the characteristic polynomial are also algebraic integers, but we also know that they are rational. So this implies that the characteristic polynomial of f is z of t. Okay? And it's, yeah. So how do we, let's finally prove this result about the eigenvalues. And the proof is very simple. And well, by the way, the independence on L follows also from this formula, because traces are independent. Now, let's prove the last assertion. So let's observe that if I take f, gamma f, view it as an element of the Néron-Severi group, and compose it with gamma, so gamma f transpose, compose it with gamma f, then I claim that this is just multiplication by the degree, q times identity, which is, by the way, graph of the diagonal map. That's the identity element in the Néron-Severi ring. So why that? Because it follows directly from the associativity of the composition in the Néron-Severi group. So you just look at the trace of gamma f t composed with gamma f and composed with any alpha. You take any alpha and take this trace. And I want to show that if you take the trace of this composition with alpha and this composition with alpha, you get the same numbers. So, and then the result will follow from non-degeneracy. So, okay, so this is just by our formula, if you put brackets like this, it will be intersection of gamma f and gamma f composed with alpha. But now, the intersection pairing is invariant with respect to, I could put identity, because it doesn't change anything. The intersection is... Мы сейчас вот это равенство доказываем. Okay. And this is the same as gamma delta x alpha. Here I have multiplication by q because this operation, this gamma composition with gamma f, does not preserve the intersection, it multiplies it by the degree. So, and this is the trace of alpha times q. So we just check that for any alpha, this number is equal to this number. But because the trace pairing is non-degenerate, it's related to the intersection pairing, and it's non-degenerate by definition, we see that we must have this property. Mm-hmm. So you can also check it directly. It's easy, but it is important that f is not just any correspondence, any element of the Néron-Severi group, but actual map from x to x. It's related to the fact that f respects the end of Poincare pairing. Okay.
Не очень понимаю, как из того, что вы длевовать,
Ну, форма не вырождена. смотри, что получается, что вот этот, что мы доказали, что этот след, он равен вот такому. Вот это равняется этому для любого альфа. Ну, да. А это, хорошо. Okay. So that means that, да. Потому что, ну что вы делаете? У вас есть два цикла. Что такое умножение на гамма-f? Это вы берете два цикла и берете просто их образ относительно f, которые действуют на одной из координат. И поскольку отображение из x умножить на x в x умножить на x, заданное по формуле тождественное на f имеется q, то отсюда следует, что если у вас есть любые два цикла здесь, если вы возьмете их образ здесь, то пересечение умножится на q. Okay, so now, okay, I have to finish, and I'm done. So it follows from this that the trace of this composition with gamma f, yes, respects the pair. Equal to q times trace of alpha t beta. Yes? So remember that this transposition is anti-involution, so it permutes these factors. And using the fact that this composition is multiplication by q, you get this result. So this composition with gamma f almost preserves the pairing, which is positive. So that trace of alpha composed with alpha t alpha is greater than 0. Да.
Дурацкий вопрос. Какое отношение имеет трейс отображений к пересечению?
А вот была формула Левшица, что это то же самое. Вот оно. Вот это то же самое, что по нашему определению, что след гамма f или мы эту формулу не доказываем, да. Это, но мы ее докажем. Это как бы частный случай общей формулы Левшица. Okay, so conclusion is that multiplication by gamma f on the neuron severity group, the neuron severity rescales a positive form by factor by q. So you have a free abelian group with a positive form, and now you have an endomorphism of this free abelian group, namely composition with this gamma f, and you know that the form is rescaled. It follows that the minimal polynomial, the one that we have here, that the eigenvalues of this gamma f, view it as an endomorphism here, are of norm q to the 1/2 roots of mx, mt, sorry, have absolute value q to the 1/2. Okay, and the roots of this polynomial are precisely the roots of the characteristic polynomial. So we know that this Frobenius endomorphism of the first Étale homology is annihilated by some polynomial with integer coefficients whose roots have this absolute value. Okay, so I'll stop here.
Which are the same modulo every L, and therefore they're integers. You can't
No, but I need to somehow relate this intersection with the trace on the homology.
No, I mean, M is independent of L already.
Sure. So for this conclusion, for this fact, we do not need anything. It just follows directly from the Hodge index theorem, which asserts positivity, and from the fact that the Néron-Severi group is a finitely generated abelian group. For this, you do not need anything, except, okay. And now you have the information about the roots of this polynomial, m. And now you want to conclude something about the eigenvalues of this f acting here. And for the last step, you really need the Lafschitz formula. You want to relate the traces, this geometric trace with algebraic one. Okay? Good. More questions? So next week, we'll start developing Étale homology theory in general. And that will be the end of so this is the end of the kind of first part of this course, this course.
Мы поймем, что вот Вологодский, который сегодня определили, это
Да.
да.
Но мы это поймем, но вот утверждение еще раз, как бы вот первая часть этого следствия, то, что характеристические полиномы не зависят от L, она в общем случае, да и здесь тоже, она оказывается невероятно вот сложным, глубоким результатом. То есть на самом деле для любого многообразия это просто неизвестно. Это известно для Фробениуса, но если у вас вот просто есть какое-то произвольное многообразие, и у него есть отображение из него в себя, эндоморфизм, что характеристический полином не зависит от L, это невозможно доказать. Над комплексными числами это тривиальный результат еще раз, потому что вот это f сохраняет целочисленные когомологии. Поэтому вы можете, а все остальные получается тензорное умножение на ZL. Ну, конечно. Да. А вот такого кольца в общем случае неизвестно, как его построить. У него есть кандидаты, но вот это как бы стандартная гипотеза, какие-то очень сложные гипотезы про алгебраические циклы в духе гипотезы Ходжа, которые... Что? Ну да. Которые нужны, чтобы вот эту картинку. Делинь это смог доказать для морфизма Фробениуса, но вот используя доказанные им все гипотезы Вейля, в том числе про собственное значение Фробениуса. Он оттуда это выводил. Вот. Хорошо, спасибо.